Okay, so hi everyone, welcome. So let me see. Okay, so the first exam is going to be October 22nd, which is 2 weeks away. And it will be on the material that we've already covered in recitation. So today's recitation is going to, I have to confirm with Clayton, but I'm pretty sure it's not going to be on the first exam. But after the first exam, the course goes pretty quickly, so we have to start this material before the first exam actually happens. But I will double check with Clayton this week about the contents of the exam. It's going to be multiple choice, it's going to be online, and it's going to be closed book multiple choice format will be used. Yeah. So the documents that, is it during class? I think so. Yeah, lecture should be Tuesday, Thursday at 8 o'clock, which is a terrible time. So, yeah, it is in class. In the past, it's in class. So I need to email Clive and see how it's going to be administered. But I think it's going to be on one of those like test taking program. I don't know. So we'll figure it out together. We're here together to do it. So it's going to be okay. But all of the contents of the first exam you can find in those 2 Word documents that we've discussed previously. So there shouldn't be any like new information. We've already reviewed all the information for the exam. So what I'm thinking is, yeah, so Wednesday's a good time because it's the day before the exam. So this week is new material. Next week, depending on how far we get this week, we might do some new material. And then the week of the exam, we will review the exam material. I think that's fair. I think that's like good. Obviously, if you have something you wanted to talk about, we can discuss that. But if no one asks, then I'm just gonna do what I want. So if you want to focus on something else, you gotta let me know. But that's what I'm thinking for the next couple of weeks of class. Okay, cool. So with that being said, I think we can begin our discussion on phase diagrams. So phase diagrams, when people think about phases, they think of like the 3, they think of like solids, they think of liquids, they think of gases. And we know that every element or molecule can be all 3 of those, right? Like, so you have water, you have ice, and you have vapor, right? So depending on temperature and pressure conditions, you can create any of those three things. So like, let's see, let's go over here. So typically, in the past, we've seen phase diagrams that are like this. Is that not good? What the hell? Oh, there we go. That's it. That's what we want. Okay, so typically we've seen phase diagrams where we have temperature here and we have pressure here. So, you know, at low, let's see if we can get this right. So we have low temperature and high pressure region. We'll have a solid phase. And then if we heat it up a little bit, we have a liquid phase. And then here we will have a vapor or a gas phase, right? So this is our phase diagram of water, right? Depending on pressure and temperature, right? And so what we see is that like we have points along which where we transition from one phase to another phase, right? So if we're in this point, we are ice, and as we increase the temperature, we form a liquid and we melt, right? We melt. And then likewise, you could go from liquid to gas, and that's evaporation, right? So everyone's kind of familiar with these ideas from our lived experience, but when we talk about phase diagrams of material science, we can talk about these three types of phases, but we also are very interested in solid phase diagrams. So these are like two different phases. These could be two different crystal systems, and oftentimes they are like one would be an FCC, one would be a BCC crystal, or they could have two different compositions. So one could be like a nickel-rich crystal, and one could be a nickel-deficient crystal. So it really depends on your system, but a lot of material science is understanding our position on different phase diagrams, and then understanding how we can manipulate our processing conditions to reach different points on the phase diagram, thus ensuring we can target certain material properties. So temperature and pressure is like great, it's cool, but like pressure is really annoying. Pressure is hard, it's fickle, right? Pressure is like really weird to control. If you take thermo, you know it's like non-linear a lot. It's like annoying. And temperature is nice. We like temperature. Temperature is easy to control. And in material science, we like one other thing. The other thing we like is chemical composition, right? So that is the that is really what we're interested in. So we're going to redraw a phase diagram. Come on, come on. So now our axes are temperature and chemical composition. And that's great, right? Because chemical composition we set at the beginning of the experiment, and temperature, you know, temperature is very easily controlled in an oven or something. I don't know. So what we know in general is that, you know, at low temperatures, we're going to have a solid phase. So we're going to call that alpha. Like alpha. And at high temperatures, we'll have a liquid phase. So we'll call it liquid, right? So, okay, cool. So, and then at some point, we're gonna like solidify. So we're gonna freeze, or at some point we're going to melt, and we're gonna, right? So at some time we're gonna be here and here, and we know the end destination, but the route is different. And like, so, but when it's not just immediate freezing or immediate melting, right? So like, if you have ice cream, right, and it's like, it's ice cream, but then like, you let it out and it's like kind of like mushy and it's like half ice cream, half melted, right? Like that happens in material science all the time. And that is, you know, a very interesting state because you have two phases present. And oftentimes, depending on where you are on this phase diagram and how fast you traverse the phase diagram, this in between region, this region of two phases, can be manipulated in order to create some very interesting material science. So typically what's going to happen, if this is our phase diagram of ice cream, right, we'll have this region of liquid plus alpha, right? Oh my God, this example sucks. Okay. So say this is where we start out. We start out in a liquid. And as we begin to lower the temperature, we begin to freeze. And we reach a point where now, once we've crossed this line, so this line is called the liquidus line. Liquidus. And that just means that we're going from a liquid phase to a mixed region. And so as soon as we start this process, now we have a mixed structure of both a solid and a liquid. And at the beginning, you know, if this is our cross section here, this is our sample. At the beginning, it's just going to be little dots of solid that participate out. And as we continue to move down through this region, these regions will grow in size, right? And what's happening during this process is that atoms, right? So I often describe atoms as having feelings and emotions, and they don't. They only respond to energy gradients, and like they want to go to lower energy states, right? So what happens is at this point, it becomes more energetically favorable for the atoms to be in a solid phase than a liquid phase. So as we continue to lower the temperature, the thermodynamics of the system change, promoting atoms to make solid atom-to-atom bonds. So as we continue to lower the temperature, atoms from the liquid region will move to these solid regions and join to them, right? And so what we have is a mixed phase. And if we are interested in knowing the composition at any point, so if we say, okay, so what percentage is liquid, what percentage is solid, using the phase diagram, we can use a technique called the lever rule. So we're at this point here, we have a mixed phase, and if we so see, we have the red and the green, and these points relate to different compositions. Right, so in this case, we haven't really discussed the chemical composition yet, but this could be for example, this could be nickel in copper, right? Percent nickel and copper, and that is also known as brass, right? And brass, as we discussed in the past, is a solid solution. So no matter what composition of nickel and copper we have, we will always have the same crystal structure. So the composition we have of the nickel, we're going to say it's 10%, right? 0.1. I don't know, I just made it up. It's 10%. But what this is saying is that that's the average of the whole the whole thing has a composition of 10%, right? but the liquid here has a composition of, let's say, 2%. And the solid phase here has a composition of, let's say, 40%, right? So what this is saying is that initially the solid phase has a higher percentage of nickel than the liquid phase and vice versa. And in that way, we can compare the lengths of these lines to get an idea of the ratio between the two, because we know that they have to average out to our overall composition of 0.1. So that is called the lever rule, where we compare this distance, right? We compare this distance to the length of the hole, and then we get a percentage that corresponds to the liquid phase. And if we compare this distance to the length of the hole, we get a percentage that responds to the solid phase. And as we traverse this line, we could see maybe down here, right? So now this line is shorter than this line, and that makes sense because we should have larger particles because we should have more of a solid phase. And then once we reach this point here, we have reached the solidus line. And now we have 100% solid structure. So this becomes, okay, everyone's like, okay, so what? Like, oh, we froze this thing and we got a solid. And you're like, yeah, you did it. But like, also, this becomes really powerful because we know that the first thing that's going to happen is we're going to form a lot of little grains, right? We're going to nucleate a lot of little grains. And then we are going to, those grains are going to grow, right? They're going to grow. And in that way, that gives us a sense of time, right? So baked into this graph, there's this other dimension to it, which is time. And if we go really fast, so if we freeze our material very quickly, what we're going to have is a cross section with a lot of little grains, right? And they're all going to be very small because we didn't give them enough time to really come together. But if we cool the material very slowly, first we will nucleate a lot of grains, and then they will all convert. They will grow very slowly, very uniformly, and then they will get really nice big grains. And so we talked about last week how grain size is a way that we can control material properties, right? We can control the strength through grain size, through the Hall-Petch relationship. So by cooling our material at different rates, we can get different grain sizes, and then we can also control the way that the structural properties of the material in that way. That's great, like, yay, we did it, good job, everyone. But most materials aren't solid solutions. Like, brass is cool, it's an exception, but most materials aren't solid solutions. And most materials, they, like, you can add a little bit, but it will get to a point where you have phase separation. And what I mean by that is, like, steel is carbon in an iron, right? And we can add small amounts of carbon to our structure and get a new phase. But if we add too much carbon, the iron and the carbon will separate, right? So a lot of materials all act in this way, and therefore we need to describe their phase behavior. And so that leads us to what we call the binary eutectic phase diagram. So let's get into it. So our axes are the same, right? So we have temperature on our y, and our x-axis is composition. Chem comp, right? And so here's going to be 0, and here's going to be 100. So we're going to say B percent B in A, right? So the percent of atom B in A. So here at 0, we have 100% A. And here at 100, we have 100% B. Cool. So what happens if we're at a really high temperature? We have a liquid, right? At a really high temperature, we've melted everything, we have a liquid. So we're going to put a giant L up there. Yeah. Now, if we are at 100% A, right? So say we're right here on this line. That's the same as the diagram we just talked about, right? So at 100% A, we have this diagram, and at some point here, right? At some point here, we're gonna have the melting point of A. Whatever that is, I don't know, but it's there. And then we're going to form the A. Below this, we're going to form the phase alpha. Now, at small percentages of impurities, we just have the alpha phase. So it might look something like this. Right? So this we'll call alpha. So in this region of temperature and composition, we just have alpha phase. So that's great, like, cool, we did it. And we can do the same thing on beta, on the other side. So at 100% B, we have the beta phase. And that will have a melting temperature here of beta, right? And then how's that look? That looks okay. Cool. So at our two extremes, we have the two phases, right? And now this is room temperature, right? This is room temperature down here. This is a low temperature. And so what that implies is that all the other temperature, at all the other compositions at room temperature, we're going to have both phases present. We're going to have both alpha and the beta phase, right? Because we're going to have both phases present. So this could take place and take shape in many different ways. So we could have small grains, you know, we could have alpha grains surrounded by beta grains. We could have kind of stripe type patterns, and we will discuss all of these, but we have segregated domains of alpha and beta in our structure. While here we have just alpha and just beta. So that's great, but also, you know, like, we know that this thing will melt, right? So we know if we're here and we go up here, we change the phase. So we have to have that intermediate step, right, that we just discussed. We need to have the liquid plus solid phase on our phase diagram. Alpha and beta are just two materials in the, yeah, exactly, Jacob, that's correct. So for example, like, there are two different elements, right? So the two different elements, and the alpha phase is the pure element A, and the beta phase is pure element B. So it could be like, I don't even know. It could be like, I'm trying to think of an example. So like aluminum and iron, right? So this is pure aluminum, this is pure iron, and here we have a mixed phase of aluminum and iron crystals. So yeah, I hope that helps. And or they could be two different phases of iron. So what we're going to see is that there's different types of steel that have different crystal structures and different chemical compositions. And we can form them. Some are hard, some are soft. So this could be austenite steel or ferrite steel, but we'll cross that bridge when we get there. But in general, it's two different elements with two different crystal structures. So when we have just predominantly the A element, we have the alpha phase, which is the elemental phase of that. Would they both have the same phase at room temperature, or we can result in mixtures at room temperature, such as liquid mercury and iron? Yeah, okay, so that's a great question. So in this case, at room temperature, they're both solids. And we're talking about two phases of solids. So liquid mercury is like a really interesting material element because it is a liquid at room temperature. So in that case, that is a mixed phase of a liquid and an ion, but it isn't. So there's this whole this kind of gets into the idea of like separability. So this is really cool. So like, you know how you have a soup? Like if you have chicken noodle soup, you have like chicken and broth, right? And carrots there and noodles. But you could pick out a carrot. Like you could pick out a carrot and take it out, and then you have a carrot. If you melt your chicken noodle soup, you heat up your chicken noodle soup, you like they're not gonna make frozen chicken noodle soup. Like so you melt your chicken noodle soup and then you freeze it, you can't re-get the carrot, right? The carrot's not coming back. Hi, Allie. So in that case, liquid mercury and iron is like the carrot in the soup. You know, you can very easily separate them. But in this case, this is like ice cream, where you can freeze ice cream and you can melt ice cream repeatedly. So you can't distinguish between the two in the same way that you can the carrot in the soup, if that makes sense. So when you mix liquid mercury and iron, you're making a mixture, but there's not like a chemical. It's not a chemical mixture in the same way when you melt two elements together to create an alloy. I hope that helps. I don't know. That might have been a stupid metaphor. But you know, in this case, we're talking about an alloy of two elements where we will have where we could have two solid phases present. And at low compositions, we have the solid is purely just the alpha phase, and at high compositions, the solid is purely just the beta phase. And in between, we have a mixture of the two solid phases. So in that way, what we also know is that if we heat everything up, eventually we will just get the liquid phase. Wait, if we heat it all up, eventually we will just get the liquid phase. So in between here and here, we would need a transition of some sort. We need a transition of something. So we can draw this line. And what we end up with is in this region here, we have alpha plus liquid. And in this region here, we have liquid plus beta. So these regions of the phase diagram are bound by the pure phases that it touches. And this makes sense because at low compositions here, we start out with a liquid. As we cool and we traverse this region, we have a mixture of the liquid and the alpha phase that begins to precipitate. And then as we eventually enter the alpha region, we will then have pure solid alpha phase. Same over here. So liquid phase, we begin to nucleate beta crystals, and then we have the beta phase. So what that says on this, if we pick a plot point here, what this says is we start to solidify, we have a liquid plus beta phase, and as we reach this point here, now we will have another phase separation occur, where now we no longer have a liquid and a beta phase, but now we have an alpha and a beta phase. So what that could look like a couple things. Let's see. So here is our cross section, right? Here is our cross section. And as we begin to participate, to freeze the material, we begin to form beta crystals in the blue, and they grow in length, in size. Right? And if we remember from the lever wall, like if we look at the lever wall here, we can see that the beta phase that we're forming is different in chemical composition than the liquid phase that we have. Right? So the liquid phase, what ends up happening is that the liquid phase has a lot more of atom A in it than the solid phase. The solid phase is predominantly composed of element B, and we have the liquid that's predominantly composed of element A. And so at this point, right on this line is where it's the most extreme, where the solid phase has this composition and the liquid phase has this composition. Right? So then what happens is we have these huge beta crystals that form, right? And as soon as we traverse this point here, then what's ever left, right, precipitates out as the alpha phase. That. So what we're left is with, what appears to be predominantly a beta phase with a matrix of alpha phase in it. And then as we are in this domain, we can still apply the lever rule in this domain. So you can look at this length versus this length and say, okay, so this here is this is the majority, this is the percentage of the beta phase we have in this material, and this here is the percentage of the alpha phase. So just eyeballing that, this looks like a 4-to-1, maybe 80% beta, 20% alpha. Okay. So this diagram is also very interesting because if we look at the liquidus lines up top here, when I was learning this stuff and I was thinking about it, you would think that like, okay, melting point of A is here and melting point of B is here. Like, okay, that makes sense. Like, I get it. But wouldn't the liquidus line just be a straight across between the two, right? Because you would think if you would have 20% B, 80% A, it would be like right here or something. But actually what we see is that there is a depression in the melting point. So there is this composition here where the melting point is lowest, right? And that is called the eutectic point, and that is where the binary eutectic phase diagram gets its name. And so if you traverse any other composition, you have to go through this alpha plus liquid phase or this beta plus liquid phase. You have to go through the transitional step. But if you go from directly on this eutectic point, you go directly from a liquid to an alpha plus beta phase, right? And so that is a very interesting example of, and in that way, if this were a cross section, so this is our cross section, and we're having a conditions where we traverse this eutectic point, and we're going to spontaneously go from a liquid to a solid, and a solid of two different phases. So to do that, atoms are going to have to respond very quickly. They're going to have to be like, oh my God, I have to make a solid. And what happens is a crystal starts to grow. We'll call that B for blue, beta for blue, right? And then this becomes a localized beta-rich region. So right next to it, we'll have a alpha-rich region. And then right next to it, we'll have another beta-rich region, right? And then an alpha-rich region. And now these crystals will continue to grow and attract more like atoms. So what happens is they start to form, they can't grow out this way anymore, so they grow out horizontally. And what we form are these grains that are stripes. So we have long beta grains, long alpha grains, long beta, and this is called the lamella structure, right? And so these grains are very interesting because of how long they are, right? So if we remember the whole Petch relationship, where we said that smaller grains are stronger because it traps dislocations. If you look at it from this direction, these grains are very small, right? So look at how small these grains are, right? But if you look at it from this direction, these grains are very long, right? So the same grain in one dimension is small and the other dimension is long. So in one dimension, the yield stress will be very high, and the other dimension, the yield stress will be very low. And in this way, we produced a material with anisotropy, which just means that in one direction is different than the other direction. So the performance across the grains is different than performance along the grains. So even though this eutectic point is very hard to reach, many times we target it for this lamellar structure. And then to do so, we produce a material that's very strong in one direction, very weak in another direction. So again, this is the binary eutectic phase diagram, chapter 8 in the book. How is everyone feeling about this? Good, yeah? I will email Clive about it. Sorry, I'll email Clive about it, the exam. I don't believe that phase diagrams will be on the exam. Typically, they're on the second exam. And like I said, the exam's on the 22nd. So next week we will continue to discuss phase diagrams. And then the week after, which is the day before the exam, we will review. So, okay. Anything else? I don't think so. The Nobel Prizes was to women, right? It was for CRISPR, right? It was gene editing, snip, snip. So I think it was Emmanuel Carpenter and Doudna, Jennifer Doudna. Yeah, okay, so they're really cool. Look up CRISPR. It's the future. It's going to change your life. It's kind of scary, but in a good way. Right? That's what it is, right? It's gene editing. So do that if you want. Not material science, but yeah. Okay, everyone, have a great week. Stay safe, wear a mask. Do get ready for spooky season. Okay, bye. And